When sizing conductors for a fire pump, it's crucial to understand the requirements outlined in the National Electrical Code, specifically Section 695.3. This section addresses the power source for fire pumps and its ability to handle locked rotor current, often abbreviated as LRC. The core principle is that if you are using a single power source, that source must be capable of supplying the locked rotor current to the fire pump and all its accessory equipment indefinitely. This means the conductors feeding the fire pump need to be sized appropriately to handle this substantial current draw. Let's break down the elements involved in this calculation. Firstly, you need to determine the locked rotor current of the fire pump itself. This information is typically found on the pump's nameplate. Secondly, you need to consider any accessory equipment connected to the fire pump circuit. A common example is a jockey pump, which maintains pressure in the fire protection system. Determine the full load amperage, abbreviated as FLA, of the jockey pump. You'll need to convert the horsepower, abbreviated as HP, rating of the jockey pump to amps using the appropriate formula or NEC tables. Thirdly, calculate the total locked rotor current. This is achieved by adding the fire pump's locked rotor current to the full load amperage of the jockey pump and any other accessory equipment connected to the circuit. The resulting value represents the minimum ampacity the conductors must be capable of carrying. Fourthly, select conductors with adequate ampacity. Refer to NEC Table 310.16 or other relevant tables to determine the ampacity of different conductor sizes and types. Ensure that the selected conductors have an ampacity equal to or greater than the total locked rotor current calculated in the previous step. Keep in mind that conductor ampacity is affected by factors such as ambient temperature, the number of conductors in a raceway or cable, and the termination temperature rating of the equipment. Apply any necessary correction or adjustment factors as required by the NEC. Fifthly, consider voltage drop. While the NEC doesn't explicitly mandate voltage drop calculations for fire pump circuits, it's good engineering practice to minimize voltage drop to ensure proper pump performance. Excessive voltage drop can reduce the pump's flow and pressure output. Size the conductors to limit voltage drop to an acceptable level, typically no more than 5%. Sixthly, choose the appropriate overcurrent protection. The overcurrent protection device, such as a fuse or circuit breaker, must be sized to protect the conductors from overcurrent conditions. However, it must also allow the fire pump to start and run without nuisance tripping. NEC Section 695.5 outlines the requirements for overcurrent protection of fire pump circuits. The overcurrent device must be capable of carrying the locked rotor current of the fire pump indefinitely. In general, the overcurrent device should be sized no less than 150% and no more than 300% of the fire pump's full load amperage. Consult NEC Section 430.52 for specific requirements on motor overcurrent protection. Seventhly, consider the type of conductors. Mineral insulated cable, abbreviated as MI, is often used for fire pump circuits due to its fire resistance and ability to maintain circuit integrity under fire conditions. Other conductor types, such as copper or aluminum conductors in rigid metal conduit, abbreviated as RMC, may also be permitted, depending on local codes and project specifications. Ensure the selected conductor type is suitable for the application and complies with all applicable codes and standards. Eighthly, ground the fire pump system properly. Proper grounding is essential for safety and to minimize the risk of electrical shock. Ground the fire pump motor, controller, and any other metallic component of the system in accordance with NEC Article 250. Use a grounding electrode conductor of the appropriate size to connect the fire pump system to the building's grounding electrode system. Ninthly, coordinate with the local authority having jurisdiction, abbreviated as AHJ. The authority having jurisdiction has the final say in the interpretation and enforcement of the electrical code. Consult with the AHJ early in the design process to ensure your fire pump installation complies with all applicable requirements. The AHJ may have specific requirements or interpretations that differ from the general code provisions. And tenthly, maintain thorough documentation. Keep detailed records of all calculations, conductor sizes, overcurrent protection device ratings, and other relevant information. This documentation will be helpful for future maintenance, inspections, and troubleshooting. Now let's put these principles into practice with a specific example. Suppose you have a 208-volt fire pump with a locked rotor current of 500 amps. You also have a 3 horsepower jockey pump connected to the same circuit. The first step is to determine the full load amperage of the jockey pump. Using NEC table 430.250, a 3 horsepower, 208 volt, 3-phase motor has a full load amperage of approximately 10 amps. Therefore, the total locked rotor current for the fire pump and jockey pump is 500 amps plus 10 amps, which equals 510 amps. Next, you need to select conductors with an ampacity of at least 510 amps. If you're using mineral insulated cable, you can refer to the manufacturer's data or NEC tables to determine the ampacity of different MI cable sizes. For example, 3 number 1/0 MI conductors may be sufficient to carry 510 amps, depending on the specific cable type and installation conditions. However, it's crucial to verify the ampacity with the manufacturer's data and apply any necessary correction or adjustment factors. If 3 number 1/0 MI conductors are not sufficient, you may need to use larger conductors or run multiple conductors in parallel. For example, you could use 4 number 1 MI conductors in parallel. When running conductors in parallel, ensure that all conductors are of the same size, material, and length. Also, ensure that each conductor is terminated in the same manner. The overcurrent protection device must be sized to protect the conductors and allow the fire pump to start and run without nuisance tripping. According to NEC section 695.5, the overcurrent device should be sized no less than 150% of the fire pump's full load amperage. Assuming the fire pump has a full load amperage of approximately 140 amps, 150% of 140 amps is 210 amps. Therefore, the overcurrent device should be sized at least 210 amps. However, the overcurrent device should also be sized no more than 300% of the fire pump's full load amperage. 300% of 140 amps is 420 amps. Therefore, the overcurrent device should be sized no more than 420 amps. In this case, a 400 amp fuse or circuit breaker would be an appropriate choice. It's important to note that these calculations are based on general code requirements and may need to be adjusted based on specific project conditions and local codes. Always consult with a qualified electrical engineer and the local authority having jurisdiction to ensure your fire pump installation complies with all applicable requirements. In summary, sizing conductors for a fire pump requires careful consideration of the fire pump's locked rotor current, the full load amperage of any accessory equipment, conductor ampacity, voltage drop, overcurrent protection, and applicable codes and standards. By following these steps and consulting with qualified professionals, you can ensure a safe and reliable fire pump installation. Now let us discuss some of the common mistakes made during fire pump conductor sizing so that you can avoid these errors. One of the most common mistakes is failing to account for the locked rotor current of the fire pump. The locked rotor current can be several times higher than the pump's full load amperage, and it's essential to size the conductors accordingly to prevent overheating and voltage drop. Another common mistake is neglecting to include the full load amperage of accessory equipment, such as jockey pumps, in the conductor sizing calculations. Accessory equipment can add a significant load to the circuit, and it's important to account for this load to ensure adequate conductor ampacity. Another mistake is using incorrect ampacity values for conductors. Conductor ampacity is affected by factors such as ambient temperature, the number of conductors in a raceway or cable, and the termination temperature rating of the equipment. It's important to use the correct ampacity values from NEC table 310.16 or other relevant tables and apply any necessary correction or adjustment factors. Also, another mistake is failing to consider voltage drop. Excessive voltage drop can reduce the pump's flow and pressure output and can also damage the pump motor. It's important to size the conductors to limit voltage drop to an acceptable level, typically no more than 5%. Another common mistake is selecting an inappropriate overcurrent protection device. The overcurrent protection device must be sized to protect the conductors from overcurrent conditions, but it must also allow the fire pump to start and run without nuisance tripping. It's important to follow the requirements of NEC section 695.5 and consult with a qualified electrical engineer to select the appropriate overcurrent protection device. Another mistake is using the wrong type of conductors. The selected conductor type must be suitable for the application and must comply with all applicable codes and standards. Mineral insulated cable is often used for fire pump circuits due to its fire resistance, but other conductor types may also be permitted, depending on local codes and project specifications. And finally, one other mistake is failing to coordinate with the local authority having jurisdiction. The AHJ has the final say in the interpretation and enforcement of the electrical code, and it's important to consult with the AHJLE in the design process to ensure your fire pump installation complies with all applicable requirements. By avoiding these common mistakes and following the guidelines outlined in this presentation, you can ensure a safe and reliable fire pump installation that meets all applicable codes and standards. Let's also explore some advanced considerations for fire pump conductor sizing. One advanced consideration is the use of reduced voltage starters. Reduced voltage starters are used to limit the inrush current of the fire pump motor during startup. This can reduce the stress on the electrical system and can also reduce the size of the conductors required to feed the fire pump. There are several types of reduced voltage starters available, including auto transformer starters, part winding starters, and solid-state starters. Each type of starter has its own advantages and disadvantages, and the choice of starter will depend on the specific application. Another advanced consideration is the use of emergency power systems. Emergency power systems, such as generators or uninterruptible power supplies, abbreviated as UPS, can provide backup power to the fire pump in the event of a power outage. This can ensure that the fire pump will continue to operate even when the normal power supply is interrupted. When using an emergency power system, it's important to size the conductors and overcurrent protection devices to accommodate the emergency power source. The emergency power source must be capable of supplying the locked rotor current of the fire pump and all accessory equipment indefinitely. Another advanced consideration is the use of harmonic filters. Harmonic filters are used to reduce the harmonic distortion caused by the fire pump motor. Harmonic distortion can cause overheating of electrical equipment and can also interfere with the operation of other electronic devices. If the fire pump motor generates significant harmonic distortion, it may be necessary to install harmonic filters to mitigate these effects. Another advanced consideration is the use of surge protection devices. Surge protection devices are used to protect the fire pump motor and controller from voltage surges caused by lightning or other electrical disturbances. Voltage surges can damage sensitive electronic components and can also cause the fire pump to fail. It's important to install surge protection devices to protect the fire pump system from these hazards. Another advanced consideration is the use of fire-resistant construction. Fire-resistant construction can help to protect the fire pump system from damage in the event of a fire. This can include using fire-resistant walls, floors, and ceilings to enclose the fire pump room. It can also include using fire-resistant cable and conduit to protect the conductors feeding the fire pump. Another advanced consideration is the use of remote monitoring systems. Remote monitoring systems can be used to monitor the status of the fire pump system from a remote location. This can allow building owners and managers to quickly identify and respond to any problems with the fire pump system. Remote monitoring systems can also be used to perform remote testing and maintenance of the fire pump system. Finally, another advanced consideration is the use of energy-efficient motors. Energy-efficient motors can reduce the energy consumption of the fire pump system and can also save money on electricity bills. Energy-efficient motors are designed to operate more efficiently than standard motors, and they can also last longer. When selecting a fire pump motor, it's important to consider the energy efficiency rating of the motor. By considering these advanced considerations, you can design a fire pump system that is safe, reliable, and energy efficient. Remember to consult with qualified professionals and the local authority having jurisdiction to ensure your fire pump installation complies with all applicable requirements. And also keep in mind that fire pump installations must be inspected and tested regularly to ensure they are operating properly. Inspections and tests should be performed in accordance with NFPA 25 standard for the inspection, testing, and maintenance of water-based fire protection systems. NFPA 25 provides detailed requirements for the inspection, testing, and maintenance of fire pumps, including weekly inspections, annual flow tests, and periodic maintenance. Weekly inspections should include checking the pump for leaks, verifying the suction and discharge pressures, and ensuring the pump is running smoothly. Annual flow tests should be performed to verify the pump's flow and pressure performance. Periodic maintenance should include lubricating the pump bearings, replacing worn parts, and cleaning the pump and motor. In addition to NFPA 25, local codes and regulations may also require specific inspections and tests. It's important to be familiar with all applicable requirements and to ensure that inspections and tests are performed by qualified personnel. Proper inspection, testing, and maintenance are essential to ensure that the fire pump system is ready to operate when needed. A well-maintained fire pump system can save lives and protect property in the event of a fire. By following the guidelines outlined in this presentation and consulting with qualified professionals, you can ensure that your fire pump system is safe, reliable, and ready to respond to any emergency. The information provided here is for general guidance only and should not be considered a substitute for professional engineering advice. Always consult with a qualified electrical engineer and the local authority having jurisdiction to ensure your fire pump installation complies with all applicable codes and standards. These are some final notes to consider when determining what size the conductor should be. It is essential to consult the specific edition of the National Electrical Code, abbreviated as NEC, that is enforced by the local jurisdiction. Code requirements can change with each edition, and it is important to ensure compliance with the current code. Verify the voltage rating of the fire pump motor and ensure that the electrical system is designed to provide the correct voltage. Supplying the wrong voltage can damage the motor and can also affect its performance. Consider the ambient temperature where the conductors will be installed. High ambient temperatures can reduce the ampacity of conductors. It may be necessary to increase the conductor size to compensate for high ambient temperatures. Determine the number of conductors that will be installed in the same raceway or cable. When multiple conductors are installed together, their ampacity must be derated to account for the increased heat. Consider the distance between the power source and the fire pump. Long conductor runs can result in voltage drop. It may be necessary to increase the conductor size to minimize voltage drop. Coordinate the electrical design with the mechanical design of the fire protection system. The electrical and mechanical systems must work together to ensure the fire pump operates properly. Consider the future needs of the facility. It may be necessary to oversize the conductors to accommodate future expansion or changes in the fire protection system. Obtain approval from the local authority having jurisdiction before starting any electrical work. The HA may have specific requirements or interpretations that must be followed. Document all calculations, conductor sizes, overcurrent protection device ratings, and other relevant information. This documentation will be helpful for future maintenance, inspections, and troubleshooting. By following these final notes, you can ensure that your fire pump installation complies with all applicable codes and standards and that it will operate safely and reliably for years to come.